everyone. Welcome into lecture number 5 of linear algebra. This lecture is on elementary and partitioned matrices. Let's start off this lecture with a little motivation. And the motivation is going to come as follows, but consider a system of the following form. So a system of equations written in matrix form. So I'll write it this way, a system of the form A times X equals B. Okay, and let's suppose, so here A we'll suppose is an m by n matrix, all right, and that means that X is an n by 1 and B is an m by 1. All right, and further let's suppose that M, matrix M, is an m by m matrix, so a square matrix that is non-singular. So remember, non-singular means that the inverse of this matrix exists, right? And we can find it, so it's non-singular. Then these following systems have the same solution, okay? So in other words, they are equivalent. Remember, that was our definition of equivalent systems. They have the same solution. But then the systems, the one that we were given, AX equals B, and this new one, which we multiply M on both sides. M is an m by capital M is an m by m matrix, so it can be multiplied on the left of A and on the left of B, right? MB on this side. These two systems have the same solution, so these are equivalent. And so the motivation here is that we can use this idea. To try to help us simplify the system. All right. In other words, one method that we might use to do this is, there are lots of methods to solve these systems of equations, especially once they're written in matrix form. But one method we could use is to, if possible, let me actually write that. If possible, it's not always possible, but if possible, we could try to find a matrix M. Again, non-singular, same scenario as what we've talked about here. Matrix M in our m by m. Non-singular. Non-singular means the inverse exists, right? Such that the product matrix M times A, we'll call it U, this is in our m by n, is upper triangular. So remember, upper triangular means that along the main diagonal, everything below the main diagonal is zeros, right? So we talked about these in a previous lecture. In this case, then our system would become, in this case, our system becomes the following. It becomes U times X, so MA times X equals C, right? Where the C vector is equal to M times B. And it's easy for us to solve an upper triangular system. It's easier, right? Because essentially an upper triangular system like this is very similar to Gaussian elimination. It's not quite, because the diagonal entries aren't ones necessarily, but it's very, very close to Gaussian elimination. So this is why we like this kind of matrix equation where the left-hand matrix is an upper triangular. So it's similar to our method of Gaussian elimination that we learned in a previous lecture. Okay, so let's talk about this. I call this motivation because this is kind of our goal. This is where we're headed, at least with the first half of this lecture. The first maybe 3/4 of this lecture is to find a systematic way of converting our system AX equals B into this new system UX equals C, where U is the upper triangular. And then, of course, the solution, we would need to do it in such a way that the solution X that we're looking for is the same, it's preserved. All right, so one of the main tools that we're going to use are something called elementary matrices, and they're in the title of this lecture. So let's talk about those next. These are pretty straightforward, but they're extremely, extremely useful as well. So elementary matrices, the plural of matrix is matrices. All right, so here's the definition. An elementary matrix is a square matrix. So it's a square matrix. Square means the dimensions are the same, right? Rows and columns are the same. Square matrix obtained So it's obtained by applying exactly 1. So exactly 1 elementary row operation, which we talked about in a previous lecture as well. So exactly 1 elementary row operation to the identity matrix of that space. Remember, identity matrices are always square, right? Okay, so we'll do examples of these, but first I want to write out the different types. Remember, we had different types of row operations. There were 3 types, and so this is going to leave us with 3 different types of elementary matrices. All right, so type 1, these types apply to both the row operations and the elementary matrices themselves. But type 1 is to swap 2 rows. So just swap 2 rows. So let's say I'll call this E1. First of all, let me write. Remember, these operations are all applied to the identity matrix. So this is going to be an example. Let's do this for a 3-dimensional matrix just so that we can see how it works. So there's our identity matrix in our 3x3. And so E1, so we're going to use this for all that follows here. So I'm not going to repeat writing the identity matrix, but a type 1 elementary matrix is obtained by swapping 2 of the rows. So for example, we could swap the first 2 rows. All right, and this leaves us with an elementary matrix, which is not the identity matrix. So this is an elementary matrix. All right, of type 1. That's a type 1 matrix. All right, type 2, we can multiply any row, any single row, right, one at a time, any single row by a non-zero constant. All right, so again, example, we'll take our identity matrix. We can multiply row 2 by some constant, let's call it k. So type 2 identity matrix might look something like this. Right? And so the only criteria here is that k is not 0. And so in this case, I multiplied row 2. You could multiply row 1 or row 3, or if it's a larger matrix, any row, but it's got to be just one row at a time, right? So this is a elementary matrix of type 2, where we've multiplied a single row by a non-zero constant. All right, there's one more type, only one more type, and that's type 3. And type 3 says that we can add a multiple of one row, a non-zero multiple, but I mean, honestly, it could be a 0 multiple, but we can add a multiple of one row to another and replace the second. So we'll add a multiple of one row to another row and replace the one that wasn't multiplied. All right, so we're allowed to multiply one row, add it to another row, and then replace the second one. So in this case, E3, maybe we take row 1 and we add k times row 1 to row 3. So k times row 1 is going to make this k0, 0. Add it to row 3, it's going to become k0, 1. And then replace row 3, but leave the rest alone, right? So a type 3 elementary matrix could look like this. And again, this time it's okay if k is 0, but if k is 0, then really you didn't do anything, right? You didn't do anything. So usually k will not be 0, but technically it's allowed to be 0. In type 2, k cannot be 0. Absolutely cannot be 0. Now, you could argue actually that if k is 0, then this isn't really type 3. This is just the identity again, right? So, you know, that's kind of subtleties, but for us, usually this k won't be 0, and it won't even be an issue, right? But we can multiply any row by a constant, add it to another row, and replace the second row. Okay, so these are the elementary matrices. These are just examples, these 3 that I've written down, but this is the general definitions of type 1, 2, and 3 elementary matrices. They're always square, so you know if you have 5 rows, you have to have 5 columns, etc. And they're obtained by just applying the elementary row operations from the previous lecture, two lectures ago, I believe it was. But the previous lecture, applying those to the identity matrix of that space. Okay? So let's look at some consequences and some examples of these as we move forward here. So this will be item 3. Here's a theorem, and this is kind of I was going to say kind of important. It's extremely important, actually, because remember, our motivation is that we want to find a way to modify a system of equations into a simpler system. Simple is kind of in quotes there, but into a simpler system. But the whole key here is that we have to multiply, when we do this, if we're going to do it, we have to make sure that the matrix that we multiply by is non-singular. And remember, non-singular means that the inverse matrix exists, which is not always true, right? Not every matrix has an inverse. So here is a fact about, in theorem form, a fact about elementary matrices. So if E is an elementary matrix, then its inverse exists. So E inverse exists. So therefore E is non-singular, right? And it is an elementary matrix of the same type. All right. Now, we could work through this in general to prove this theorem, because every theorem should technically be proved. But I just want to sketch the proof by some examples, which, is not the proof, but I just want to go through here. I'm going to actually cross this out. Examples. So we'll call these illustrative examples. These are not the proof. All right. It's an exercise for you guys to go through and actually prove this in general, but I think you'll see based on these examples exactly how the proof is going to work. All right. So let's suppose that we're working in our 3x3, just for the sake of this argument again. And so let's go through all three cases. So case 1. So E is type 1. All right. So then it turns out that E is its own inverse. So for example, again, I said this is just going to be examples. I'm not going to write out a proof here, but let's suppose that this elementary matrix is the one that we started with up above, right? So we obtain this matrix by swapping rows 1 and 2. How do we get back to the old matrix that we started with? We swap rows 1 and 2 again. So it turns out that E inverse does the same exact thing. So we are going to swap back rows 1 and 2. Oh boy, I wrote the identity matrix. So we have to actually, I swap them, right? But the matrix that swaps them back, right, is the inverse. So a type 1 matrix is its own inverse. It's its own inverse, okay? So that's a very special case. So swap 2 rows. How do you undo a swap of 2 rows? You swap them back, right? So here's case 2. Let's suppose if E is type 2, I don't need to write this out, but let's suppose E is of type 2. So let's say E looks something like, again, in 3x3. Let's go with the one that we wrote before. And remember, our rule was that k is not 0, right? So we multiplied row 2 by k, by this non-zero constant k. How are we going to undo that? Well, we're going to multiply through row 2 by the reciprocal of k, right? By 1 over k, or the inverse, you could say, of k. And so in this case, the inverse of a type 2 matrix that looks like this is a type 2 matrix whose entry in that same row is the reciprocal of the original, right? So if this is 2, this is a half. If this is a half, this is 2. And those two matrices are inverses of each other. All right, so again, we can work this out. You guys should write out the details. And, definitely one thing you should do is justify these claims that I've made, right? So that means multiply these two matrices together, and if indeed these are inverses of each other, then what should you get? Well, you should get that E times E inverse is the same as E inverse times E should be the identity matrix in all three cases, right? So that's something that you can definitely take a moment and check as you work through this lecture. All right, case 3 is the last case, right? Remember, this one was type 3 was we took a multiple in our example up above. We took k times row 1 and we added it to row 3. All right, we want to undo this. Well, what did we do? We multiplied row 1 by k and added it to row 3. So how are we going to undo that? We're going to multiply row 1 by negative k and add it to row 3. Or you could say we could multiply row 1 by k and subtract it from row 3. But that's not how the rule works, right? So it's got to be multiplied by negative k and then added back to row 3 again to undo this k that's here. So the inverse of a type 3, where this entry here is, again, say 2, will end up being a negative 2. Subtract off that row that you added on. Okay? So again, make sure you can work this out, multiply these together, add them up, see what happens, you know, and you will find that these matrices are inverses of each other, and clearly the type 1's inverse are themselves, so that's the same type. Type 2, the inverse is also type 2. Type 3, the inverse is also type 3. Okay? So the whole point here, though, the key to all this is that the inverse of an elementary matrix exists. So elementary matrices are non-singular, and they are, again, elementary. Okay, before we do an example, let's give one more definition, and then we'll do an example together here. But the following definition is very important, again, to our motivational example that we laid out at the beginning, or our motivational pathway, you might call it. Here's what it says. So a matrix B is said to be row equivalent. And so this is the key here. We want to make sure that our matrices are row equivalent when we're solving systems. So it's row equivalent to a matrix A if and only if there exists what we'll call a finite sequence of elementary matrices. That's just a list, right? A finite list of elementary matrices. And so the dimensions have to match up in a certain way. I'll write an example here in a moment. But elementary matrices, so these matrices will be like E1, E2, all the way up through EK. There's finitely many, so we can write down a final one. And these have to obey the following property. So B is row equivalent to A if these matrices work together to make the following true. That B is equal to, the way this works is multiplication from the, on the left. So it's going to be A times E1 on the left times E2 on the left, all the way up through EK on the left. So left multiplication, in this case, the order is going to matter to some extent, okay? And so this is the definition. They're row equivalent if you can convert A into B by multiplying by a sequence of elementary matrices. All right? So that's our definition. Now, just to unpack the definition, what has to be true? Well, A and B have to be in the same dimensional space, right? They have to be n by n matrices. They don't have to be square. However, the elementary matrices always need to be square, and since they're multiplying on the left here, they need to be in the space Rm by m, all of them, right? So each one of those has to be a square matrix, elementary matrix, that's dimension m by m for left multiplication to work out. Okay, so here's a theorem. So we can now just refer to two matrices as row equivalent, and now we know what it means, right? One can be converted into the other by applying elementary row operations or by multiplying by elementary matrices. So each one of these multiplications by an elementary matrix is going to perform an elementary row operation, the one that's, you know, specific to how it was built. It's going to perform that operation on A, and that's going to leave us with a different matrix, right? A matrix B, which we'll call row equivalent to A. All right, here is our theorem, though. Let's let A be an n by n matrix. And because of this definition, we can say the following. So the following are equivalent. And here are the items. Number one, A is non-singular. Remember, this means that A has an inverse matrix. It has an inverse matrix that we can write down. We can find it, right? So that's item number one. Item two is that A times x equals 0. This is called the homogeneous system, right? A times x equals 0 has only the trivial solution. And the trivial solution is that x has to be 0. A times 0 is equal to 0, right? So homogeneous systems are always consistent. Hopefully you saw that in your studies in the last section. But this always has the trivial solution. Sorry, it only has the trivial solution. Every homogeneous system does have the trivial solution. The key to this statement is that this system has only the trivial solution. There is no other solution to this equation, a times x equals 0. Okay, this is the only one. And then number 3, this one now comes from our new vocabulary, that A is row equivalent. A is row equivalent to the identity matrix. To the identity matrix I. All right, and so the proof of this is a recommended exercise. You should work out the proof of this to show that, you know, if A has an inverse, then the following two are true, and then vice versa, right? Because they have to be equivalent. So here is a corollary, though, and this is a corollary. Corollary means that it should follow directly from this, and it does. Okay, so this system, A times x equals B, has a unique solution. So this means it has a solution and only one solution, right? Exactly one solution. Has a solution, but not infinitely many, right? So it has a unique solution if and only if A is non-singular. Okay, so there's a corollary of this previous theorem. So if A is non-singular, then it's row equivalent to I. We can get the x by itself, right? So that's the idea. If A is row equivalent to I, then we can perform elementary row operations to make this be I times x, identity times x, and as we do it to both sides of the equation, right? And that's one way to solve a system of equations like this. All right, so the key to this is that we can, you know, the act of, so let me write this down. So this then tells us, and we've kind of already talked about this, but not in exactly the same language as we're doing now. But so let's say we're given a matrix A in Rn by n. Then we can say if A is non-singular, then we, according to this, right, it must be row equivalent to I. Then we can do the following. We can find, so then there is a sequence of elementary matrices E1 through EK such that, look what we have, EK times EK minus 1 down to E2, E1, A is equal to I, right? Well, whatever this is then, this product of these elementary matrices must be A inverse, right? This must be A inverse. So this gives us a way to compute our A inverse as a matrix. So we can perform the row operations, gather, keep track of the row operations that we did, write down the corresponding elementary matrices, and then once we're done, that product of those elementary matrices, that's got to be our A inverse matrix. Because remember, if we have a matrix times A that equals the identity, then that matrix has to be the inverse, right? Has to be the inverse, provided it exists, which is the only way you'd be able to get this equation anyway. So what I would like us to do is I'm going to give us a matrix. So here's a matrix A. 1, negative 1, 2 in the first column. 4, negative 2, 2 in the second column, 3, 0, 3 in the third column. And so if I want to compute, is this non-singular? And if so, find the inverse by doing the following. So we can find the inverse using the augmented matrix, or just by using row operations if we wish, right? To change this into the identity matrix, but find the inverse using elementary row ops. And then I want you to keep track of the operations to build the inverse. So I don't think I said this exactly what I mean, but what I want you to do is perform the row operations to convert this to the identity matrix, right? So changes to the identity matrix by performing only elementary row operations. Keep track of each row operation, and then use those elementary matrices, the corresponding elementary matrices, to build, right, just like this, to build the inverse matrix. So give it a shot, and then you can unpause it if you get stuck, and we'll do it together. All right, now that you've had a chance to work on this on your own, let's work on it together. So our job here is to start with the matrix itself and perform some row ops to turn this into the identity matrix, right? So I'm going to do this in exactly the same way that we would do kind of Gaussian elimination, and I'm going to write out all these operations and I'm going to number them, okay? So the first thing I want to do is I'm going to do two operations at once. It's going to result in two different matrices. And I want to get rid of these. I want to zero out these two terms, right? So what do I need to do? Well, as a type 3 operation, I need to do row 2 plus -1 times row 1, and then replace row 2. So that's a type 3 operation, right? So I've just changed the order of how we talked about it before, but I'm going to add a constant multiple of one row to another row, and then replace the row that wasn't added, right? So that's going to get rid of this one. And then, that's not exactly right though, sorry. I want to add just one. Just add those two together, right? Add those two together. And then same thing with number 3. This time I need to subtract, right? So row 3 is, I'm going to add -2 row 1s and then replace row 3. All right, so those are my first two elementary matrices, and we'll write these out in a few moments, but after performing this, I'm going to have a 1, a 0, a 0, a 4, a 3. All right, that's exactly how this works. And now, what am I going to do? Well, this, I have to actually do this, right? So I have to actually add these up for the first row. So this will be 2, this will be 3. And then I have to subtract, right? This row minus 2 times the first row. So this row minus 2 times the first row, that's gone. This is going to be 2 minus 8, so minus 6. And then 3 minus 6 is going to be -3. All right. Okay. So now what do I have to do? Now I have to get rid of this one. So this one's going to be my third elementary matrix. It's going to be row 3 plus, this time I'm going to add 3 times row 2 to zero this out, and then replace row 3. All right. So again, 1, 4, 3, 0, 2, 3. This is all good. This one's now going to be 0, 0. And I'm adding, again, 3 times row 3. So that's going to be 9, 9, right? Plus -3. So that's going to be a 6. Okay? At this step, now, my fourth elementary matrix, I need to make this term a 1, and I can also make this term a 1. So my fourth and fifth I can do in one step of this, but it's going to take two elementary matrices. So I'm going to replace row 3 with 1/6 row 3. And I'm going to replace row 2 by 1/2 of row 2. Okay? So I'm just performing these row operations one at a time. So again, my first row, it stays the same. Second row, I divide by 2, essentially. So 1, 0, 1, and then 3/2. And then this one's going to be 0, 0, 1. All right, and now I can go up and take care of these two. This is like the Gauss-Jordan step, right? So essentially we've done Gaussian elimination. Now we want to do Gauss-Jordan elimination. And so let me write down, this is going to be 2 more, right? So this one's going to be my 6th elementary matrix and my 7th elementary matrix. So what's it going to be? So this one's going to be row 2 plus, this is going to be -3/2 row 3 and replace row 2. So right there, right? And then this first one's going to be row 1 plus -3 row 3, replace row 1. All right, and notice both of those, because this is the Gaussian elimination, it's just going to zero those out and not do anything else over here, right? All this is taken care of. So scroll up. Let's see what we have now. We have 1, 4, 0. We only dealt with row 3 there, so it doesn't change anything else, right? So 0, 1, 0, 0, 0, 1. And we have only one more step, right? So this last step, we need to take care of this. So this is our 8th elementary matrix. So 8 is finite. It feels like a lot, right? But it's finite. So this one's going to be take row 1 and add -4 times row 2, replace row 1. All right, and so this leaves us with our identity matrix. Now, because we could do this, then that means A is non-singular, right? Because we were able to do this process with only these elementary row operations, then we get this. Now, we need to write down the matrices, right? Here, I'm going to change the color of this one just so that we can see how these matrices line up. So any step that we did 2 matrices on, those you can change the order. It doesn't matter because you're doing both of them kind of at the same time. But otherwise, we have to work from backwards, right? So we have to do this one before we do these, etc. And so to write out our matrix then, I'm just going to write these in order. The elementary matrices for each of these operations are going to be as follows. So this is going to be E8 times, I'll just write it out in colors, and then we'll write down the matrices, times E7 times E6 times E5 times E4 times E3 and then times E2 times E1. This is, of course, going to end up being our inverse matrix, right? So let's see exactly what these matrices are. This one, we're going to subtract 4 times row 2 from row 1. So this matrix will be 1, -4, 0, 0, 1, 0, 0, 0, 1. That's exactly what this tells us to do, right? And so then we just keep going. We write out all these matrix products. So this one, we're going to take away row 3 from row 1. So this will be 1, 0, -3, 0, 1, 0, 0, 0, 1. All elementary matrices. You know, again, at the same time, we could have done this one. So this one's going to be take away 3/2 of row 3 from row 2. 0, 0, 1. Then we get to our green operations here. So again, we can do these in either order, but I'll go in the same order that we went before. So I'm going to take 1/2 of row 2, right? And then I'm going to take 1/6 of row 3. Whoops, 1, 0, 0, 0, 1, 0, 0, 0, 1, 6. And then I still have 3 more matrices here, so I'm going to actually give myself more room. All right, so this blue one says this is a type 3. Notice I didn't use any type 1 in this process. We could have if we wanted / needed to, but we didn't, right? So there's only type 2s and type 3s. We're left with a couple type 3s left here. So this time we're going to take row 3 and add 3 row 2 to it. So 0, so we're going to do this to row 3, right? So this is going to be 0, 3, 1. And then the last couple are going to be, we're going to take row 3 and subtract 2 row 1. So -2, 0, 1. And then the last step is to add row 1 to row 2, right? So 1, 0, 0, 1, 1, 0, 0, 0, 1. Okay, and so now to get our actual matrix, we have to multiply all of these together, right? So it's a bit of work. So let's do it. All right, so I just took a moment there and multiplied together a few of these by grouping. So I multiplied together the first 3 of these to get this matrix, and then the last 5 of these all together, just very carefully multiplied those together to get this matrix. And at this point, we can just multiply these together now. And so what do we get? Remember, it's first row times first column. When we add this up, we get 1 -2 -4 thirds. That's going to be -7 thirds. And then as we go across the top row, we end up with the next one's going to be -2 + 2. So that's 0. And then finally 4/6, which is the same as 2 thirds. Then we go across the next row. So this one's going to be 1 plus, so this is going to be 1/2, right? 0 plus 1/2, and then plus another 1/2. So that's a 1. And then the next one is going to be 1/2 -3/4, so that's -1/4. And then finally, this last one is going to be negative 1/4 as well, right? 3 and 6 cancel, so negative 1/4. And then along the bottom, we see this row is just 0, 0, 1. So this is just going to pick out the third row. So negative 1/3, 1/2, 1/6. And so this should be our inverse, but if we, I mean, it's perfectly fine, but it's got these fractions in here. So one thing that we could do is factor out a common denominator, which in this case we have 4, we have 2, we have 3, so it's got to be 12, right? So we take out this 12, and then let's see what's left, right? This is then going to have to be negative 28, 0. This one's going to be 8. The second row is going to be 12, negative 3, negative 3. And the last row is going to be negative 4, 6, and 2. All right, and so this is our A inverse. Now this is kind of done the long way, but the point is that this is how it works. And you can now check. You can multiply this times the original A and make sure that you get the identity matrix back. But the point here is that we can build our inverse matrix by elementary row operations and then using the elementary matrices themselves. Now, what we probably should have done, right, is use the augmented matrix method as we went through, and it would have built this matrix for us anyway, right? We would have gotten this out of the augmented matrix method that we learned in the previous lecture. And if we just kept track of the row operations, we could have still written this product right here. So this product is kind of the most important thing. The act of multiplying it together is just a little exercise at the end, but getting the inverse as a product of elementary matrices was the point of this exercise, and that's what we got here. Okay, so there's one more thing that I'd like to talk about in relation to these elementary matrices, and that is the LU factorization. So this is very important in computational methods. So the LU factorization. And this says the following. So the idea is that we want to suppose that A is an n by n matrix, and that it can be transformed by elementary row operations into an upper triangular matrix. So now it's a square, right? So suppose this can be transformed not only by elementary row operations, but only by type 3. So by type 3 row operations only into an upper triangular matrix U. Okay, so in other words, we have A is equal, A can be transformed into U, right? So by that I mean it's row equivalent to U. So our U can be determined by doing row operations and type 3 only. We've restricted to type 3. We'll do an example here. But type 3 only times A, right? That these will end up being a product of elementary matrices times A, and that will give us U. And the idea is that because we're doing type 3 operations only, then to transfer this into an upper triangular matrix, each of these matrices will be lower triangular. So each of the E's will be lower triangular. And lower triangular matrices are preserved by matrix multiplication on the left, we'll say. All right, so what we end up with then is that this matrix, we know it's invertible, right? So this is, we'll call it M. This is non-singular. Right? And so what we can do then is we can factor our matrix A into the product. So then A would be equal to M inverse, get rid of this, times U, but this matrix M inverse will be a lower triangular. So the whole idea here is that we're going to find a lower triangular matrix by doing row operations to transform A into an upper triangular. That result will be our U. And then we'll get our L by taking the inverse of this product here that gives us M. And it turns out the product is very simple. Sorry, the inverse is very simple to compute for the lower triangular as well. So lower triangular are very nice. And that's one reason why this method is used extensively in computations. Okay. And so again, what does this look like? Well, the whole idea is that the lower triangular, by the way, our lower triangular is going to have just ones along the diagonal, zeros up here, and then could be anything in this triangular region down here. Those are zeros. Our upper triangular is going to have anything up here, including the diagonal now. So the diagonal does not have to be all ones, but it's got zeros below the diagonal. So we've got lower triangular times upper triangular equals A. So it's a factorization of A. All right, and so the real reason for doing it, though, is that the inverse, this M, this inverse of L, this can be used to transform our equations, as we talked about before, right, at the very beginning with our motivation, because then we can take our system AX equals B, and we can convert it to this system UX equals M times B, right? And so we'll have upper triangular, this will be a vector, we'll be good to go. All right, so let's do an example just to show how this works and how we can kind of easily work through this. So let's say we have a matrix A given by first row is 4, 1, 3, second row is 2, 1, 4, and the third row is 1, 3, 2. And we want to find the LU factorization. That's what we're told to do. So find the LU factorization. So step one is just to use elementary row operations to make this into an upper triangular. So we will do exactly what we did on the last example, except we won't go the whole way. So we don't have to do nearly as much of the work. So there's our A, but we'll color code it the same way. So actually I'm going to color code it by entry alone. Okay, so let's start with this one. This is in the row 2, spot 1. So I'm going to name this. Let's call it M21. It's in the second row, the first column, right? So what are we going to do? What's this operation tell us to do? How are we going to get rid of it? We want to zero this out, right? So we want to take row 2. There's the 2. We want to add to it something times row 1. There's the 1, and then replace row 2. Well, it's going to have to be a negative 1/2, right, to be able to zero this out. So we're going to add a negative 1/2 to this to zero this out. And then we're going to do the same thing with the next one, right? So this is in the 3, 1 position. So in the 3, 1 position, we're going to take row 3, just look at the numbers, 3, add something times row 1, and replace row 3. Well, this one's got to be a negative 1/4, right, to zero this out. And we'll apply these operations. Okay, so what's left? We have 4, 1, 3, 0, 0. We need to work out the rest though, right? So 1 minus 1/2, that's 1/2. 4 minus 3/2. 4 minus 3/2, so 4 has 8/2. 8/2 minus 3/2 is 5/2. And then down here, this one's going to be 3 minus 1/4. So that's going to be 11/4. And this one's going to be 2 minus 3/4. So again, that's 8/4 minus 3/4. That's 5/4, 5/4. All right, and the only thing that we have left to do now is to eliminate this term. And this term's in the 3, 2 position. So this is going to be our M32. All right, and how's this going to work? Well, we're going to take our row 3. We're going to add to it something times row 2, replace row 3. Again, 3, 2, 3, 2, replace row 3. What's it got to be? Well, it's going to have to be negative 11/2, right? Negative 11/2 on this one to get that to work. So negative 11/2, and then let's see what happens here. So this is going to be 0. This is the only one we need to compute at this point. So it's going to be 4, 1, 3, 0, 1/2, 5/2. 0, 0. Then we have 5/4 minus 55/4. So that's minus 50/4 or minus 25/2, right? Okay, and so this is our upper triangular matrix. So this is the U. This was our half of our goal, right? This is half of our goal. So this is our U. And remember, the way that we set out to get this was we were trying to find M times A to give us U. And the M is going to be a lower triangular, and its entries are going to be 1, 0, 0. M21, 1, 0. M31, M32, 1. And these are exactly the numbers that we put in these boxes, right? Boom, boom, boom. These are exactly the numbers that we put in these boxes. So our M is the matrix then, 1, 0, 0. It's negative 1/2, 1, 0. It's negative 1/4, negative 11/2, 1. All right, so this is a lower triangular matrix which converts our A, when we multiply through, converts our A into this upper triangular matrix U. But this is not the matrix L, right? The matrix L is the inverse of M. And I'll leave it to you to show that to convert from M to L. To find the inverse, we just have to take the negations of these. Remember, we said the inverse of a lower triangular, a type 3, right, is just you put the negation of these terms in there, and when you, it turns out when you multiply this through, because it's lower triangular, that you end up, these don't combine. If it's upper triangular, they do combine, and it becomes messy. But for a lower triangular, they don't. And so L is just equal to M inverse, and it's going to be given by, this is a general formula here, and then I'll write down the answer, but negative M21, 1, 0, negative M31, negative M32, 1. And if you have a larger matrix, you can see how this is going to extend, right? And so our lower triangular matrix is just 1, 1/2, 1/4, 0, 1, 11 halves, 0, 0, 1. All right? And so this is L. And so the key here is that we have now written our matrix A, right? We have now factored it into a product of a lower triangular times an upper triangular. So it's 4, 1, 3, 2, 1, 4, 1, 3, 2. And this equals, in the factored form, 1, 0, 0, 1/2, 1, 0, 1/4, 11 halves, 1. And then the upper triangular has no rules about the diagonal. So the upper triangular, this matrix, we'll see as we move forward in the semester, this upper triangular encodes a lot of information about the matrix A. The lower triangular encodes information about how to transform from one to the other, right? How to get between them. But this is the LU factorization of this matrix A. Okay, so the last topic that we'd like to talk about in this lecture are partitioned matrices, and these are pretty much exactly what they sound like. And we've already seen some examples of them. So this is item 7, partitioned matrices. So we'll just go pretty quickly through this. I'll show you some examples of how we can do some algebra with different types of partitions, and then we'll do one example at the end. But this is, like I said, pretty straightforward. So the basic idea is that we want to partition or divide up our matrices into submatrices that make it easier for us to work with, and we've already seen some examples. So we've seen examples of augmented matrices, right? So we have, say, augmented matrices of the form M equals A, and then we just drew a vertical line, B, right? Where in this scenario, A was an M by N matrix. This is for solving our systems of equations, right? And B was an M by 1. All right, and so together these made an M by N plus 1. There's one extra column, right? The extra column is B. And so that's a partitioned matrix. Now, with this kind of partition matrix, we didn't actually use it to do anything that we hadn't already done, right? But we've seen other examples as well. So here's another example. So if A is an M by N matrix, then we talked about we can write A as a vector of, as a vertical, a column of its rows, right? So a column of its rows. This would go to AM, column of its rows, or we could write A as a row of its columns. And then there would be N columns, right? And so either one of these can be thought of as a partitioned matrix as well, because the entire matrix itself is M by N, but if you just kind of divide it up into its rows, then you end up with a vertical column vector. And if you divide it up by its columns, you end up with a horizontal row vector, at least in how you can write down the matrix itself. So, like I said, these are some examples of partition matrices that we've already seen, but let's look at some other examples where we can actually, so maybe where the point of the partitioning is to help us do arithmetic. By the way, we did use the row versus column definitions to help us define what it means to be matrix multiplication, right? So we kind of have already done that as well. But let's look at these examples, like I said. So examples. These examples are going to be illustrative of the different possibilities of how we can partition our matrices and how it's going to work. So let's suppose we have the following. I'm going to say just in general, let's suppose that we have a matrix A that's m by n and a matrix B that is n by r. Okay, so we can multiply A times B in this scenario, right? Because the inner dimensions match up for A times B. All right, so I'll call this case 1. Let's suppose that we have two submatrices. B1 is a matrix that is n by t, and B2 is going to be a matrix that is n by r minus t. So we've kind of divided up the columns of B, right, and kind of split them in half. So this means then that B is going to be equal to this matrix B1, B2. You can draw a bar here if you want, but this partition matrix. And then the question is, can we multiply A times the partition matrix? How's that going to work? Well, we definitely can, right? So A times B is going to just be the dimensions of A match up with each individual, right? And the columns will match up accordingly. So this will be a partition matrix itself, AB1 partition AB2. So the dimensions all match up, right? And so this one is in M. So this part right here is in Rm by T, and this one is in Rm by R minus T. And altogether the product is in Rm by R, right? Which is what it has to be because it's still A times B. All right, so there's case 1. Case 2, what if we could do the same thing with A, except we have to be a little more careful, right? We have to maybe divide up, instead of the columns of A, we want to divide up the rows of A. All right, so in this case, let's let A1 be in Rk by M, we'll say. Sorry, K by N. K by N. We're dividing up the M. So K by N, and then A2 will be in Rm minus K by N. And so our A will look like a partition matrix this way, A1, A2. This is not a fraction, so actually I'm going to leave the line out of this one because, like I said, it's not a fraction. I don't want it to be confusing. So it's just A1, A2. And then this can be multiplied by B. So same deal, right? A times B is going to be A1, A2 times B. Each of these have n columns, A1 and A2. So they can each be individually multiplied by B. And our matrix, our product is going to be a partition matrix itself. A1b, A2b partitioned the rows so that the first one is K by R and the second one is M minus K by R. So this one's K by R and this one is M minus K by R. So it's partitioned through the kth row and the K plus first row. Okay, there's a couple other possibilities. So for case 3, we could partition each of these A and B at the same time. So in this case, we want to partition the rows of A and the columns of B, but we want to do it in a way that is pretty much the same. Sorry, I said that wrong. We want to partition the columns of A and the rows of B, but we have to do it in a way that matches up. All right, so let's remember A is in Rm by N. B is in Rn by R. We want to partition the N. So that's what I was trying to say. I didn't say it super well, right? But we want to partition the N here. We have to make sure that if we're going to do this, that these have to be partitioned the same way. Okay? So if I say, all right, I'm going to partition the columns of A, so that A1 is partitioned to be M by S, then B1 has to be in RS by R. So those have to match up. All right? Same thing, if I do A2, it's going to be the rest of it, right? So it's going to be M by N minus S, and then B2 is going to have to be in Rn minus S by R. And so the idea here, again, is that all of these dimensions match up, right? Dimensions match up. Then what we can do is our A will be partitioned, it's partitioned by its columns, so it's going to look like A1, A2. B is partitioned by its rows, though, right? So this one's going to look like B1, B2. And then when we multiply these together, look what happens. A times B. is A1, A2 partitioned by columns, B1, B2 partitioned by rows, and it ends up being A1, B1 plus A2, B2, and each of these is going to be m by r. M by r, m by r, m by r, right? And so this is equal to AB, right, which is in the proper space. M by r space. It's not only in the proper space, it turns out to be the exact right answer, but I'll let you guys work out the details of that and do some examples as you work along. But this partitioning does work. So it's almost like, it looks almost like matrix multiplication, right, of partition matrices, but the answer itself is a matrix in this case. So it's just a way, it's a computational tool, right, of breaking up your problem into pieces that maybe, hopefully, some of them will be easier than others for you to solve. Kind of save you some writing. All right, the last case is going to be the most, at least for us, the most crazy that we would do, so the most involved. So let's say we break up each of our matrices into 4 blocks, which we'll label just like portions of a matrix, but these are themselves submatrices, all right? So our matrix A, we want to break up the rows of A into K and then M minus K. And then the columns of A into S and N minus S. All right, and we want to break up B in a similar fashion. But again, now we have to be careful. So what do we have to make sure we match up? If we go back to our highlighter, we have to make sure that these terms, right, the number of columns of A have to match up with the number of rows of B. So that's what we're going to have to be careful of when we write this one out. So let me finish writing this. B11, B21, B12, B22. Again, partitioned. And so to make this all work, we have to make sure, just based on what I've highlighted, that the rows of A are partitioned the same way the rows of B are partitioned the same way the columns of A were partitioned. So the N minus S and then the S have to match up with each other, right? Now, as far as, so we could partition our rows of A however we wanted. We can do the same thing with the columns of B. So we can say that maybe this is T and R minus T. So partition the columns of B however we want. Now, how do we multiply these together? Well, A times B is still got to be an M by R matrix, right? But it's going to be partitioned as well. And how is it going to end up being partitioned? Well, in this upper left block, it's going to end up being A11 times B11 plus A12 times B21. That is the entire entry in this block. And that is a what? That's going to be a K by T matrix, right? That's K by T. The S's get canceled. And the N minus S's get canceled. So K by T, K by T. You can see just by doing this, right? K by T. In the next entry up here on the upper right, it's going to end up being K by R minus T. Right? So again, K, M minus K, T, R minus T. And so what's going to end up here is going to be A11, B12 plus A12, B22. All right, and then you can check all these dimensions add up. It's all going to work out, and this matrix up in this corner is going to be a K by R minus T matrix. All right, you can fill in everything else that's going to happen here. It's pretty straightforward, right? So this is going to be A21, B11 plus A22, B21. This is going to be A21, B12 plus A22, B22. All right, so this is the general idea of how partition matrices work and how we can do arithmetic with them. So let's end this lecture with an example, and this will be it for this one. So what I would like us to do here is to compute A times B as a block product, I should say. I said blocked, I think, but as a block product. All right, where these are blocks. So when you chop this up into 4 pieces, those are called the blocks. Even in 2 pieces, it's called the blocks. All right, so here's the deal. A is equal to 1, 1, 2, 2, 3, 3, 1, 1, 1, 1, 2, 2. I've kind of read that off as a block, but you can, there's no blocks designated on that one. B, however, there are blocks designated. So this is given in 4 blocks. So 1, 1, 1, 2, 1, 1, 1, 1, 3, 1, 3, 2, and then 1, 1, 1, 2. So here's what I'd like you to do. Take a moment, decide how you're going to partition A to make it so that it matches up with B, so that you're allowed to do the multiplication here with B. And then from there, work it out, and I'll check in with you, and we can finish this one off together and finish off this lecture. All right, now that you've had a chance to work this one out, let's try to figure out how we're going to multiply. So as we look at this matrix right here is a 4 by 3, right? It's a 3 by 4, sorry, 3 by 4. 3 rows, 4 columns. This one's a 4 by 4, right? And so what we have to make sure that we match up with is how we partition the columns of A compared to the rows of B, right? That's how it works. Columns of A compared with the rows of B. And as we do so, we notice, right, that we've got this partition. So we've partitioned B, we're given the partition of B into 2 rows and then 2 rows. So that makes it so that we don't have a choice of how to partition the columns of A. The columns of A have to be partitioned into 2 columns and 2 columns. From there, it doesn't matter what we do, actually. So we could leave this as an entire block in this sense, or we could divide the rows any way that we want, actually. It doesn't matter. So we can do the blocks any way that we want. And any way that you chose is fine. So this is the only required, this magenta here is the only required partition that we need. All right? So, yeah, let's just leave it like this, honestly. And just, we don't have to do any more, so let's not do any more. So let's see. We're going to end up with partitioned matrix, right? So AB is going to end up being, well, we need to have 4 pieces here, actually, right? So we need to have 4. So let's put the partition in after all. We can either go here or here. So I'm going to do it right here. It doesn't matter. You can choose either one you want, but I'm going to put the partition here to preserve this block of all 1s up here. Again, not for any particular reason, just because it looks good. All right, so let's compute then. So remember how this works. This corner up here is going to be this matrix times this one plus this one times this one. Right? So, by the way, if we had just left off and ignored partitioning it this way, then we could ignore this partition right here, right, for the columns. So, it doesn't, but anyway, it doesn't matter because I'm putting this partition in right here. So, again, if we just go by the rules up there, it's going to be this matrix. I'll just write out all the pieces, right? So 1, 1, 2, 2 times 1, 1, 1, 2 times, or plus, sorry, this matrix 1, 1, 1, 1 times this one, 3, 1, 3, 2. That's what's going to go there. This is going to be a large computation, right? What's going to go here is going to be this row times this column. So 1, 1, 2, 2 times 1, 1, 1, 1 plus 1, 1, 1, 1 times 1, 1, 1, 2. All right, and then we go to the bottom here. So this one's going to be 3, 3 times 1, 1, 1, 2 plus 2, 2 times 3, 1, 3, 2. Same thing here. 3, 3, 1, 1, 1, 1 plus 2, 2 times 1, 1, 1, 2. And now we just work these out, right? So I'll do it in steps, but this one's going to be the matrix. This one's going to be 2, 3, 4, 6. This one's going to be 6, 3, 6, 3. Then we'll add those up. Up here, this is going to be 2, 2, 4, 4. Plus 2, 3, 2, 3. Right? This one's going to be, 6, 9. And this one's going to be 12, 6. Right? 6 plus 6, 2 plus 4. This one's going to be 6, 6. And this one's going to be, what, 2, 6? 2, 4, 4, 6, right? 4, 6. And then we combine this all. Now we're going to end up with our partitioned matrix. So when we add this up, this is 8, 6, 10, 9, 4, 5, 6, 7, 18, 15, 10, 10. Okay, and so that's how this works. So this is our product AB. At this point, you can drop all the partitions and you'll have the answer as just a 3 by 4 matrix at this point, right? But this is how it works. All right, guys, I hope you enjoyed this one. I'll see you guys in the next one.